Okay, welcome back to another LETHEP seminar. This week we have Subham Dutta Chowdhury, who's a fellow postdoc at the TIFR, and he's going to tell us about classifying 4 Gluon S-Matrices. Shubham,
Right.
take it away.
Yeah. Thanks for setting this platform up during this such testing times. It's good to have a forum like this. And so today I'm going to tell you about some aspects of classical scattering amplitudes, like classifying, say, the 4 gluon S matrices. I'll I'll first start off with some general intro motivation as to why it's interesting to study these classifications, and then I'll present the classification not in too much detail because I don't think I'll have the time, and but of course you are at any point welcome to stop me and ask questions if you have doubts. I'll pause at regular intervals if you and give you the opportunity also to ask questions. So this is this this set of work. This work has been a part of a series of earlier works with these collaborators over here, and some on part of ongoing work with also another graduate student, soon to be a postdoc from IIC. Um, now, so what are we? So what am I going to tell you guys now? So in this talk, I'll be interested in mostly classical tree-level scattering amplitudes of the form this given by this. You guys can see my cursor, right?
Yes.
Yeah, of this form. Like you have several incoming particle elastic scattering processes, all right? And in general, depending on external states, intermediate particles, these are usually Lorentz invariant and gauge invariant functions of the polarization tensor as well as the momenta. Let us, for the moment, primarily focus on 4-point scattering, which is the thing that I'll classify. And it's basically a classical classification program that I'm aiming for. Like, what are the possible, uh, tensor structures with simple poles that one can write down, provided your external particles are, say, gauge fields or gravitons or even colored scalars, whatever. Why is this interesting? Why do we like, I mean, apart from what is the interesting bit apart from classification? So this is the meat to the skeleton. Like I won't be like explaining in detail any of these things, but just for motivation, right? So, well, one reason for studying this classification is to address the problem of classifying consistent classical theories of gravitation. And what do I mean by that? So this has been motivated by some algebraic observations that there is only a finite set of classical gravitational theories which are well behaved in the sense, like, the vacuum is stable, factorizes on poles, causality and positivity of energy, and so on. Many such things. These have been studied extensively. But the observation is that, like, the set of classical gravitational theories is finite. And in particular, it is of the type, it is basically of 3 types. That is, you have the Einstein S matrix coming from root GR. Then you have the type 2 string theory S matrix and the heterotic string theory S matrix. And these are all in the limit G coupling, the string coupling going to 0. It can be shown like that, like, if you consider the full 10-dimensional theory and you perform some compactifications in this parametric limit, the like the string scattering amplitudes, they truncate to a classical sector, and I mean, and there, that's it. Like there are no other, like, gravitational theories that we know of, like, which have such nice behave properties. So this algebraic observation, like, led us to, like, propose this bold conjecture one, which I'm not going to, like, like talk in detail about. Like this just serves as some sort of motivation. But once you assume that this can be true, there are two subsequent more interesting conjectures, and perhaps more tractable. Is that, like, the only this is the conjecture two, which is that only consistent classical gravitational S-matrix whose exchange poles are bounded in spin is that of Einstein S-matrix. What do I mean by that? I mean that if I don't allow exchanged particles to be, rising with spin, like that, you don't have a the spins going off to infinity, and you truncate them at a particular spin, say, number. Uh, this Such a truncation is inconsistent unless you include, like, the entire tower of higher spin operators. And this this, like, I mean, in turn implies this third conjecture, which is that the only consistent classical gravitational S matrix with only gravitational exchange pole, graviton exchange poles, is the Einstein S matrix. Now, in the last two conjectures, like, this, what, like, you might ask, what is meant by a, what do you mean by this consistency conditions? Apart from whatever you have for a nice theory, like, null energy conditions and, like, stability of
Can
vacuum.
I ask a question?
Yeah, sure.
When you say classical scattering,
Yeah.
I'm a bit confused. So you mean only tree level? Is that what you mean by
Yes,
classical?
yes, tree level, only simple.
Okay, I see. Okay, okay.
So this consistency conditions that was outlined in the previous section for conjectures 2 and 3, it turns out when we are talking about, say, 4-point scattering, when we are specializing to 4-point scattering, is related to chaos bound. Let me just briefly review what the statement says. So chaos bound is essentially a bound on the growth of out of time ordered correlators. This, it can be shown is that it can be shown that for a Lagrangian theory, this implies bounds on flat space scattering in the Rayleigh limit. All right. Now, this is strictly for a Lagrangian theory, this relationship that I told you about. But anyways, and it has been suggested by many people, like Maldacena, Schenker, Stanford, Kamano, Edelstein, Maldacena, Zhigodev, uh, Cornalba to some extent. And what we proposed is that Lagrangian theory, whether it has a Lagrangian CFT dual or not, any flat space scattering amplitude in the Rayleigh limit, which is the largest fixed T limit, is bounded by this growth behavior. It cannot grow faster than x square. All right. This is still at a conjecture level, but like we will we just ran with it because there were sufficient evidences that this was true, and we made a complete classification and constraining of photon and graviton 4-point flat space S-matrices using this conjecture. So there were two parts to the thing. One was the classifying what such this set of S-matrices were, and then putting bounds on them. Now, it is a bit disappointing that, like, such universality classes by default from some structural argument, one can say that cannot exist for Gluon S-matrices, in the sense that using this argument you can't say that, okay, Yang-Mills is the only allowed Lagrangian Gluon Lagrangian that you can have. Any other modification to it will violate some physical principle. We don't have that. But nevertheless, the first part of the problem, that is the classification, remains an open and interesting question. That is, like, what is the possible set of Gluon S-Matrices that you can write down. Basically, all possible tensor structures that you can write down. Gauge invariant tensor structures. Do you guys have any questions at this point?
Shubham, I have a question.
Yes.
Can you go back to your conjecture one and explain it, please? Because I didn't completely get it.
So basically what we are saying is that we want to look at all the classical gravitational S-matrices that you can write down. All right. And so far, hello? Yeah. And so far what we are from observing examples in the literature, say in the string theory literature, it's that you have three different kinds of gravitational S-matrices. One which is generated by Einstein gravity. Then you have the type 2 string theory S-matrix, graviton S-matrix. And then you have the heterotic string theory S-matrix. These three things are completely unrelated to each other. I mean to say that they are not, they are linearly independent of each other. And any other classical S-matrix that you give me can be expressed as a linear combination of these three S-matrices. Say, for example, at the level of 4-point functions, right? And we are saying that there cannot be any other classical gravitational S-matrices. This is a very bold conjecture, by the way. We are not saying that this must be true. It could be very well false, but just as a motivation to our classification problem, we mentioned this. But our main points were conjecture 2 and 3, which we were actually able to show. Conjecture 1 is purely a conjecture, say.
I see, thanks. So you're also saying that, for example, some FR gravity models or something, all of them should be discarded.
FR theory means that you have, you have R cube type of interactions, right?
Yeah, in general, you could have anything.
Yeah. So in general, using conjecture 3, we rule out that such theories cannot exist.
I see. Okay,
they have bad growth behavior.
I see. Okay.
Sorry, Shubham, just checking. So it's not really conjecture 3 then, right?
Right. I mean, but no. Important point that this conjecture 2 and 3, they're supposed to, we are hoping this hold for all point scattering amplitudes. You see, but we have been only able to prove this for 4-point scattering amplitudes.
So are these sorry.
No, go on.
Yeah, so are these conjectures true non-perturbatively or perturbatively?
What do you mean non-perturbatively? You mean?
I mean the scattering amplitude, is it some perturbative at each ordering perturbative corrections in some perturbative parameters?
No, I think he's just looking at tree level. There's no perturbation.
There is no loops.
Okay.
Yeah.
Can I make a comment on that? I mean, my understanding was that in gravity, even loop level contributes to classical scattering. This is what I thought was true.
No, why should loops? I mean, classical S-matrices is you take root GR, expand in G plus G plus H.
Right.
Maybe.
So
yeah,
so I mean, in all field theories, usually, I mean, only the tree level contribute to classical. But I thought gravity alone, there are some funny things. I think, I mean, I'm not 100% sure, but there was a talk by Bjorn Bohr where he mentioned this as a point. So I think Manu also gave a talk a long time back.
But that was Anish. But that I mean, I'm not sure about massless particles that involved massive. The external particles were massive particles there. They were mediated by long-range forces, which were gravitational forces.
I see. Okay.
I'm not sure about when you have external massless particles also.
Yeah, I thought this was not the case. I mean, because you see, I mean, the moment you have loops, you will have this log singularity, log and non-analyticities in your for massless cases, right?
Yes.
I mean,
yes.
And I have only I'm saying that only non-analytic piece is a simple pole. That's also a simple pole, not a multipole. I mean.
Right, right.
I
No,
think,
I mean, I understand the statement that you're looking only at tree level. I
Yeah,
completely agree. I actually agree with that. My only confusion was whether that is classical or not. That is my only confusion.
like I mean, any class this, signature of like quantum corrections, like just from amplitude, like structural arguments, you can see that it will come with some other type of non-analyticities other than simple pole,
Right,
like
right.
log s or something like that. All right.
I see.
So
Okay.
like I mean, simple poles. I mean, I don't think like you can have a loop thing which contributes to like a
I
simple
mean, I
pole.
agree. I
Yeah.
agree. I mean, like, I agree that the simple poles and tree level, there is, I mean, that connection I understand. My
Yeah.
only connection is between tree level and the word classical. But maybe I mean,
Yeah. What I
I'm
mean
wrong.
by
Yeah.
classical is that like I'm looking just like scattering amplitudes with simple poles. Like let's
Okay,
just
okay,
fix
okay.
on that
Yeah,
definition.
yeah,
And
okay.
probably a related vague confusion I have is like when, like for example, Ashok does this, Ashok Arnab, Biswajit, and
Mm.
they did this classical radiation. What I understand is they had some contribution to this log omega term from the
Yeah.
loops also,
Yeah.
right?
Yeah.
So, and that would give you the classical scattering in the sense of like what is the scattering in the of gravitational waves in our world, if we ask, like
Like
what is the
let
classical?
me just say that I'm not considering any loops. That is my definition of
Okay, that is
classical
fine. Yeah.
tree level S matrix.
Okay, sure.
All right, like tree level S matrices. That's the thing. Like,
Hey,
Fine,
Shubham,
fine.
yeah.
just a question. So conjecture one is basically quite bold, right? That you are not doing anything
No,
related to
no, no.
conjecture one.
I don't think. Well, although like there was a paper today trying to attempt something of this sort, right? By Yutin Huang and some people, folks, like trying to
Okay.
bootstrap kind of this thing. But let's not go into that thing. But
Okay.
yeah, as far as I know, like nothing of the sort in conjecture one has been
Yeah.
explored.
So basically, conjecture one is truly a conjecture, which you are
Yeah,
not even attempting to address in
for
this.
sure, for sure. Yeah.
And the other thing is, you will not be looking at diagrams which are intermediating uh, massive particles.
No, no, you can have massive particles, but those massive particles must be bounded in spin. That is, you can't
So
have
but that gets ruled out by CMZE, right?
that gets ruled out by CMZ. Yeah, 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 yeah.
So basically,
yeah.
you'll be looking at 4-point gravitons with point vertex, no exchange.
Yeah, yeah, yeah. I'll come to that.
Okay, fine.
Sure.
Yeah.
Yeah.
Shubham,
Yeah.
so I have a question. So in the next slide,
Yeah.
so maybe you mentioned this. So this chaos bound, because
Yeah.
I'm not familiar with this. So
Yes.
should I think of it as some average null energy condition or something, or like
No,
what
no,
is
no.
it physically?
Average null energy condition gives you a much larger bound on your
I see.
CFT spectrum. All right.
I see. So
This is
physically,
real.
how do I get the chaos bound?
So chaos bound you can think of as the growth of out of time ordered correlators, like because of some analyticity properties of thermal correlators, like in
Okay.
like the thermal plane. Mallasina Schenker Stanford showed that if you consider an out of time ordered correlator in a CFT or in their result was for quantum mechanics, although, but doesn't matter. Like if you take out of time ordered correlator, its growth behavior with time is like bounded, basically.
No, that is fine. But like,
Yeah.
but suppose I found some amplitude where that does not happen. Like, what is it violating? Like, what physical principle is it violating?
No, that it doesn't. It does. It means that, I mean, if it does not grow, that's fine. I'm just saying that if it grows, but it's growing faster than the allowed rate, then it's bad.
Yeah, I mean, what is the bad thing about it? Is what
I think it's related to some non-unitarity. Like the
I see.
theory is not unitary anymore.
Okay.
And
Thanks.
like that, I think you will find some discussions in like this related discussions in CEMZ. Like
Okay.
the line of reasoning is very convoluted actually. Like, so what
Okay.
CEMZ, like the Kamenholm, Edelstein, Maldacena, Zhigotev showed is that, all right, if you have like they basically were working at the level of 3-point function, and what they essentially showed that, like, unless you have, these gravitational terms like suppressed, say r square and r cube term suppressed parametrically, you will violate causality. Like if you have a scattering experiment, like against a like you have a scattering experiment, the
Okay.
phase shift in the iconal limit, which is basically dual to like the time delay of a probe particle traveling in a gravitational shockwave background, that turns out to be positive. Like,
Okay.
so then causality gets violated, and
Okay.
they have some arguments relating that this is somehow related to this A square growth, the chaos bound.
I see.
Actually, there is a simpler way to put this relation between OTOC bound and the Regge limit. So if you had like let's say finitely many spins and you are exchanging 4 to 4 graviton scattering, but you're also exchanging finitely many spinning particles, the Regge limit will grow as proportional to the spin of the highest spinning particle. Okay.
No, that is not true.
Why? Regge limit would be dictated by the highest.
That is only in the T channel. For the other two channels,
that's fine, but you will be adding all the channels, right?
Right.
So then it will grow. The growth will be dictated by that.
Yeah. So I'm saying that statement is not true. That in Regge limit for gravitational particles, external states, the Regge limit grows as s to the power j. Even for graviton exchange, you can show that it might grow faster. That's what I'm saying.
No. I'm saying that if you're exchanging spinning particles, the growth is dictated, and if the number of spins are like bounded, let's say finitely many spinning particles, the Regge limit grows. The Regge limit is dictated by the spin of the highest spinning particle. This is a
no. That is not true. I don't think so.
No, it is true, because this is the standard argument which is given in the introduction of your standard, what's that, string theory textbooks, right? The motivation for string theory.
No, I don't know about string theory, but like for sure, like if you explicitly compute such scattering amplitudes, you will find that in the T and U channel, the behavior actually depends on the spin of the external particles also. And that's how it gets violated for us. Like, I mean, I can discuss in detail that, but that result is not necessarily true. Like that, if you take the full amplitude and look at the Regge growth behavior, it's s to the power j, where j is the spin of the exchange particle. That is not true if you have external spinning states. In fact, like if you have just look at graviton exchange, and you have vertices coming from Bose-Bonnet and R-cube term, the spin exchange is spin 2, right? But you will find that the amplitude grows faster than a square.
No, I'm not considering any Gauss-Bonnet terms. I'm considering just kinematic exchanges, like Klein-Gordon equation level exchanges of higher spinning particles. Then the Regge bound grows like is dictated by the highest spin of the exchange particles. This is the standard statement that is used. So that's why you need infinitely many spins if it has to grow as the spin of graviton, which is s squared.
Maybe there is some misunderstanding going on, but maybe we can come back to this later. But
I was mentioning this because this is directly related to how OTOC bound is computed. The fact that OTOC bound is bounded by 2 pi by beta can be understood as an iconal scattering close to the horizon.
Yeah, but but it's iconal scattering of scalar particles. For scalar particles, you don't see this issue. What I'm saying is for spinning external particles.
No. So OTOC bound is independent of the spin of the external particle.
No,
it's so regarding
it is.
Okay. Maybe we can discuss this later.
Yeah.
So, but also like I thought from the slide that from OTOC bound you get this.
Right. I am from OTOC bound. I get this, but like OTOC is for scalar particles. Actually, one doesn't know like a priori if you have spinning particles how the bound might be modified. So that is why this classical Rege growth was a conjecture, like in the sense. And in fact,
Shobham, 1 second.
Yeah.
So therefore I was just saying that I don't want an explanation backwards. Like I wanted to just know like what OTOC is motivated by. That's all. Yeah.
No, sorry. Can I just?
Yeah.
So I think that Rohan, do you mind if we postpone this discussion to after the talk?
Yeah, I'm cool. Yeah.
Cool. All right.
Yeah. Yeah. So like I mean, so basically, like for the moment, let's just take number one as equation number one as some sort of a bound we're just going to impose. It's observation motivated. There is certain hints of it from OTOC, chaos bound growth, and so on. And like using this, we did a complete classification of this thing. And for Gluon S-Matrices, I mean, one can show that.
Shubham, can I ask a quick question?
Yeah.
Yeah. Is this all for
sure.
4-dimension, or your classification is dimension independent?
Sorry. Hello. I missed your question.
Yeah. Can you hear me now?
Yes.
Yeah, I'm saying that is this all for 4 dimensions, or is your classification?
It's dimension independent.
Okay.
Yeah. So another question, interesting question, is that of bulk locality. Like, so what do I mean by that? So consider for a moment that we are working in a Lagrangian CFT with a local bulk pool, and let us look at the excitations in the CFT that are coincident. So in the CFT, you have excitations which are coincident. You have OP sort of stuff happening. Now, it's not a priori clear whether the dual excitations in the bulk, they interact, how they interact. And like just from CFT observations, whether the bulk is lower. Like in 2D, like for example, like there have been studies regarding this. Like I'm not very sure. Like I mean, I don't know them in detail, but I know of studies being done. But in higher dimensions, usually it's very difficult, like extending those techniques to higher dimensions. And now the question is like that, even though locality at radius scale, you have the CFT techniques to understand it. Sub-ADS locality needs better understanding. And one of the earliest attempts at quantifying this question, these are just words, right? What bulk locality, all stuff. Like, so what is the concrete question you want to ask? So first attempt at this was put forward by Himsker, Kolchinsky, Penedones, and Sully. And like they found that questions of sub-ADS locality is base frame in terms of CFT 4-point function. They were motivated by the observation that from past studies that in order to retrieve flat space S-matrices in ADS CFT, the CFT correlation functions need to have some specific singularities. So like you can't just give me any CFT correlation function and like expect that, okay, you have a nicely defined bulk to it. There are some constraints. So basically bulk locality puts some constraints on CFT 4-point function. As a zeroth order, so they had a very bold proposal. Usually in known examples of ADS CFT duality, if you have a weakly coupled gravity dual, you know that your CFT has a sparse spectrum. That is the single trace operators greater than spin 2 have large anomalous dimensions, so that the spectrum is sparse. Now, they suggested the reverse proposal that any Lagrangian theory with a large higher spin gap should have a weakly coupled gravity, right? And so, in order to do that, in order to quantify that, what they did was they assumed a Lagrangian CFT involving just a scalar field O and its double traces, and tried to solve for crossing of these 4-point correlator at order 1/n square. Now, what they find is that the number of undetermined solutions to the crossing equations at order 1/n square with a finite supporting spin is one-to-one correspondence with bulk 4-point contact. So you need something in the bulk to, like, make sense of your CFT crossing function. So like some consistency conditions of your CFT is giving rise to is telling you that you must have some local bulk theory. This must, I mean, I'm not saying that this is like, essentially proving locality that, must have, but it's a nice toy model to explore. So another one of the motivations of classifying these local S-matrices is that this bulk locality can be extended to photons, gluons, and more ambitiously gravitons. All right.
Can I ask a question?
Yes.
I'm not very familiar with this terminology, but what does sub-ADS locality mean?
It means in the bulk, like, you are not in the boundary. You are, say, near the center of ADS. Say.
I see. Okay. So
yeah.
That's what is meant by sub-ADS locality.
Yeah.
Okay. Thanks.
Right. Any questions on this? Like, these are the two broad motivations for, studying these sort of classification problems, because like first has its own flavor regarding causality, but the second one also has a different, more interesting flavor, like since, like, you want to classify such bulk terms and match consistency conditions with your local CFT crossing, your boundary CFT crossing, you need this sort of this thing. So are there any questions? Like,
yes, Shubham, so what would be the exponent of S for the case of photons and gluons from the OTOC bound that you described in your previous slide?
It depends. Like, so photons, so suppose that I'm taking some particular bulk contact term, all right?
Okay.
Some bulk particular, say trace F square, right?
Yes.
And I think it grows as S in the regime, all right?
Okay.
So, for example, like if you put derivatives on trace F square, obviously this will grow faster, because this contracted derivatives will contribute to S, like the Mandelstam invariance. Right?
So is it right to say that the bound cannot be anything more than S square?
Yeah. That's what we are claiming. Like, there is not a rigorous proof of equation 1. It has been motivated from different observations. Like, it's a conjecture at the present, that, and a well-motivated conjecture in the sense that if you look at Einstein S-matrix, it satisfies this. If you look at Virasharo-Shapiro amplitude, it satisfies like S to the power 2 minus some constant alpha prime correction. So, like, there is a strong reason to like think that, yeah, this is perhaps true. Right, and in some recent work that I'm doing with Shiraz Suman and Somangshu, who is another postdoc. Suman is a student at TIFR. We are trying to show that even for spinning particles, at least for large N theories, you have the chaos bound is not more than S square, right? Because if you have external spinning objects in your this thing, because these like they have different vector indices, right? You can have like probably some anomalous growth coming from the Lorentz boosts of the spinning indices, right? What we are trying to show now is that like that doesn't happen, and still the chaos bound is still S square, like. All right. Is that clear?
Yeah. Thanks.
Yeah. So now, like, let me as a warm up thing. Like, let's see how do you classify 3 gluons category? And for 3 gluons category, it's very simple actually, because there are no kinematic invariants. Like, there are no Mandelstam invariants, and like, it's just a finite parameter set. Basically, two like, you can just using gauge invariance and using gauge invariance and homogeneity of epsilons, you can write down these two uh, 3-point Gluon amplitudes. And it turns out that, like, I mean, these are
one
the...
question, Shubham.
Yeah.
Sorry. So when you mean 3 gluon scattering, shouldn't that vanish on shell, or are these off shell amplitudes?
These are on shell amplitudes. Why should they vanish?
Because if they are dependent on the Mandelstam variables,
yeah,
because of momentum,
they are not. They are not dependent on. There is no Mandelstam invariant, right? I mean, in 3-point scattering, because you don't have ST all at 0, because this is a massless, right? I mean,
right.
Yeah.
I mean, from momentum conservation, I think you can show that this will go to 0. I think. Like, I mean, if you have like
I am not saying anything about the reality properties of the momenta.
Okay.
Okay. So these are in general complex moments.
Yeah. This can be complex momenta. Yeah. Yeah, I agree. For real momenta, you can't find, like, I mean, at least, like, so the problem appears is that, like, I mean, if you choose real momenta, I think you will find that your epsilons need to be complex or vice versa, like, or something like that. If you try to solve for the consistency conditions, that epsilon dot k is 0, k square equals 0, you will find that either of them go to, so you can't have, like, you know, a real set of this thing. So I agree. Like, I'm not saying anything about the epsilons or k's. I'm just imposing equations of motion and kinematically classifying 3-point functions. All right?
Yes.
So what we see is that, like, in general, the most general S matrix then becomes, you know, a 2-parameter set. You have one thing from the Yang-Mills and the other from the F cube type of term. All right? And therefore, this is a 2-parameter set, and this was easy to classify. But you see, for 4 and higher point scattering amplitudes, you have the Mandelstam invariants. And then you have an infinite number of kinematical invariants. And so therefore, a real infinite number of real parameters. So how does this one take care of? Right. So what I'll be telling you primarily is analytic S matrix, but like later on we will see that using our classification you can describe non-analytic. I mean, the 3-level pole exchanges also using the same basis set. Basically.
Shubham.
Yeah.
I mean, this might be a stupid question, but the 3-point Yang-Mills vertex that you had written, there were 2. So the first one, that is just the usual, that just comes from the vertex.
Yang-Mills, yeah.
Now you said that there was no loop contribution. So, but how do you get a F cube, like from a, if I were to derive it from some loop contribution, like if I do some renormalization or something, will I not get a loop contribution which looks exactly like that?
You will, sorry. Say that again.
I'm saying like the F cube term, the trace F cube term. Can I not think of it as like some loop correction to the Yang-Mills Lagrangian, basically? If I do some renormalization, can I not get that?
Sorry, can I say something?
Yeah.
I was under the impression that the way Shubham was looking at it, it was sort of like looking at all possible terms in effective field theory.
Right.
So I don't know, Shubham, maybe you can say this better, but I was under the impression that the goal is not to say, let's start off with Yang-Mills action.
Yeah.
And then let's see. The goal is really to say, I start off with gluons. Those are my particles. It's very S-matrix kind of stuff.
Yeah.
Start off with gluons, and then you say, what are the allowed interactions?
I mean, in fact, like what rewarded in your language, what I can tell you is that, like, if you compute the loop corrections of your Yang-Mills action, you will land up, and still you are looking at 3-point amplitude. All you will get is a Yang-Mills times some momenta function plus some momenta function times a F cube. So I'm really just saying that I'm classifying possible tensor structures that may appear.
Okay.
Like, yeah.
I see. Okay, take it, fine.
Yeah. So let me get back to analytic S matrices. Like, so how does one construct? What do I mean by analytic S matrix? So, like, so let me just explain it for photons. That's the easiest. I don't have to go into complications. So in particular, say I have a particle P of mass M and representation R of SOD. And well, I mean, you can easily take SOD minus 1 comma 1, but like the representations are for calculational purposes, it's good to work with Euclidean, and let's just weak rotate to Minkowski. So I'll be just my calculations will all be in Euclidean, and then I'll like you can, since it's Lorentz invariant, you can just go to Minkowski. Now how does one do this? Get a tree level scale estimate? Well, the photon amplitude. Suppose you have a you're looking at photon amplitude with a particle P exchange, and what you do is like you take two off-shell photon P 3-point functions, glue them together using the P propagator, and that's your S matrix, right? And two different S matrices constructed in this manner only differ by terms which are proportional to, say, S minus M square in the S channel, for example, if you're stitching in the S channel, for example. Now, this analytic terms that they differ by are what I'm calling this analytic S matrices. That is, you take your amplitude, take away the poles, what you're left with is the analytic S matrix. And it's a polynomial in S, T, and U and the polarization tensors, and it's seemingly infinite. You can just have an infinite number of such terms. And our purpose in this talk would be if we can successfully classify these analytic polynomials in S, T, Mandelstam invariants as well as the polarizations to be in a controlled manner. So interestingly, like there seems to be like, I mean, the idea of our classification will be to grade these things by their order of derivatives. So I can write a partition function, containing the information of the S matrix at each derivative order. So I can write down something like equation 5. What does this mean? Suppose I give you a partition function like this corresponding to a particular scattering amplitude. What this will tell you is that suppose you are looking at particular derivative order M. Nm tells you the number of linearly independent S matrices that can exist for those external particles at that derivative order. All right. So this is the classification that we will do. And is that clear? Like,
no, I don't understand. Can you say that again, please?
Yeah. So what I'm saying is that like we are trying to classify polynomials of S, T, and U, right? And polarizations, right? Now this can be anything, like a very large number, right? But we are looking for an organizational principle such that you can encode it in terms of just the counting, at least in terms of a partition function like ZS matrix, such that if I tell you that, okay, this is my you have 4 external photons, and I want you to tell me that how many linearly independent S matrices are there at say 8th order in derivatives of a photon S matrix. All right. And you just Taylor expand this ZS matrix about x is equal to 0, look at x to the power 8 and tell me that, oh, this is the number of linearly independent S matrix at that derivative.
So when you say derivatives, you mean like the number of momenta
correct,
that come?
Correct.
Okay, that's I'm good.
So yeah. Is the idea to find n?
Yeah, exactly.
Okay.
We will not only find n, we will find like what, like each of the structures which are given by n. Like suppose n tells you that n8 is say 6, I will be able to tell you what these 6 structures are also.
Okay, I see.
So will you also be making any statement based on some other principles that this expansion sort of truncates? I mean, after
yeah. you will find that like this can be written down as a very compact expression, some
I see. Okay.
GP series kind of expression. So
I see. Okay.
yeah.
So
Like,
M is the number of external particles that you.
No. M is derivatives, number of derivatives.
Okay.
I have not. I have not mentioned like the. So from now onwards, I am working only for 4 particles category. So unless like I mention otherwise, I think Z S matrix will always refer to 4 particle S matrices.
Okay.
Yeah.
Fine.
So now, like since I've made clear
just one small small
yeah.
thing. So X, just for clarification, X will be the Mandelstam invariant variables, and N would contain all the polarization data, right?
No.
So you can have polarization, dotted with some p's raised to some power also.
No, so X will. So suppose you have a scattering amplitude, right? So it's a polynomial function of STU as well as epsilon and p's, where epsilon and p's are dotted amongst each other. Epsilon dot p, right?
Yeah.
X M counts all the instances of P, including the Mandelstam invariants, STM. So S will be X square, all right? P will be X square, U will be X square, while epsilon dot P will be X.
Okay, I see. Okay, thanks.
And so this is just a counting partition function, all right? And the way we decode our tensor structures out of this thing is I will come to that using some S3 properties of your this thing. So let me just go ahead and you'll understand how we approach the thing. Right?
Yeah, sure.
Yeah. So now you have these polynomials of S, T, and U as well as the polarization tensors. Now we further require Lorentz invariance, gauge invariance, and S4 permutation invariance also for photons. For gluons, we also of course require the group G singlets, like of the gauge group. So what is the data that I have at my disposal? So I will be trying to build up the S matrices by default. All right. So how do I go about this? First, we have the Mandelstam invariant, which is fine. Then you have polarizations and gauge invariance associated with the gluons. So since gluons have this color index also, like the polarizations have color index also, it's gauge invariant and it has 2 sets of gauge invariants. Like one is the non-constant gauge invariance, which is this second one, which is like the usual photon like, and then you have the usual gauge, constant gauge transformation, where you have a gauge transformation of this sort, right? And so therefore, like motivated by this, like we can think of the adjoint value polarization tensor as a tensor product like this, where you decompose epsilon A mu to be just a photon times a color structure. And the invariance, gauge invariance translates to the fact that taus transform in this manner, where epsilons transform in this manner, right? And
so what does this internal symmetry R stand for? I didn't get that.
So this is the transformation group for the transformation matrix for the color index.
But aren't you dealing with photon here only, or gluon?
No. I'm saying gluons. I'm just now going over to gluons.
I see.
Right. So gluons have a color index, and for example, like for SUN, this RAB will be like ABC theta C epsilon. Yeah, FABC theta C. Yeah, like that. Right.
Yes, I understand.
Yeah. So this nice structure, this at the linearized level, tells us that we should think of the S matrix as a tensor valued product over photon S matrices and some scalar color S matrices. So summary is that we have the Gluon S matrix as a tensor product of photon and scalar S matrices. We want the photon S matrix separately to be gauge invariant, Lorentz invariant, and S4 invariant, while the scalar S matrix must be the group G invariant, that is the group G under which your the gluon fields were charged, and then you have the S4 invariance also. And we apply these in steps. Well, the gauge invariance part was immediately clear. You now absolutely realize that the photon S-matrices must come from local Lagrangians of the form which is built out of F's, right? And then you have you apply these in steps.
Can I ask a question? What was epsilon mu A in the photon S matrix, or is that just a typo?
Oh, sorry. I meant, well, no, not really. Like, I meant what I meant to say is that, like, this is really a tensor product. Like that tau A contracts with the epsilon mu A, right?
If it were to contract, then shouldn't the A no longer be there on the left-hand side?
No, why? So think of it as this: like you have your usually you have this in usually scattering amplitudes, you have this the color part which is separate, like which is TA, trace of TA, TB, TC,
right.
TD, and then you have the photon part, right? Which is
right.
FA, FB, FC, FD with particle levels. So this A represents that FA.
Right. But in that, the left-hand side that does not have an A index anymore.
Yeah, no, Shubham.
Oh, sorry. Yeah. I am sorry. Like this 9 on the left-hand side, you shouldn't have this A because, like, this A index has been contracted. Yeah, this is a no, but you get my idea, right? What I'm trying to say, that like.
No, sorry, Shubham. Can you just go back to the previous slide?
Yeah.
I think the point here is like the line above equation 8, right?
Sorry.
Yes.
So you basically have an epsilon mu A. It's a polarization tensor that has a space-time index and a color index. And you're writing that as epsilon mu tensor tau A, right? And so
you're saying
what
that is
Anish is saying is that epsilon mu is the guy that like shifts by momentum. And then the tau A is the guy that rotates the color this thing. That's why he's saying that on the next page. So I think that's correct.
So that, okay. I understand. This is confusing. I agree. So what I meant to say is that I will take just purely a photon amplitude and multiply it with a color structure.
Okay.
Where the photon amplitude is really that of a single photon. Like there is no color structure that you need to worry about there.
Right.
So is this decomposition not exact? Why do you have like a plus dot to dot?
That is just like, other terms. You can have other similar structures like you just. A scalar is not unique, right? In the sense that you can have S1 scalar, S2 scalar, like different color structures. It's just like, Is that clear?
I think Shubham, what you mean is that the right-hand side, S photon times S scalar, is an example of the kind of term that appears in the gluon.
Correct. Yeah. It's not. Yeah.
Can I ask another question?
Yeah.
So in for example, in the case of the Yang-Mills that you mentioned, that you have this 2 parameter set A and B for 3-point amplitudes.
Yeah.
So let's say for some general this thing, you might get, let's say, some n parameter set, that is the n of m. How are you sure that one of the parameter is not coming from, let's say, like a field redefinitions of some other parameter?
So like the field redefinitions, field redefinitions basically mean that you are applying equations of motion, right? If you take your Lagrangian, off-shell Lagrangian, you perform a field redefinition, what you are left with is something which is proportional to your equation of motion. So if you impose your equation of motion, which you do for tree-level scattering in order to find that, you take care of this field redefined terms automatically, right?
I see.
So take the example of scalar. Sorry, am I getting cut off or is Anish getting cut off? I'm not able
No, I was thinking. I mean, I hadn't complete. I mean, I didn't finish my thought actually. So yeah.
Yeah, Anish's voice is a bit breaking. Yeah.
Okay.
Not too much, but yeah.
Yeah.
Can you repeat that answer? Hello.
So what I'm trying to say is that suppose you have two different Lagrangians, all right? Say, for example, like let's just start with scalars, all right?
Okay.
So you have two Lagrangians and you apply field redefinitions to one of them.
Okay.
And due to the field redefinition, what you will get is that you'll get some higher order terms, like because depending on how you field redefine, you will get some higher order term, and then you will have a same 4-point local counter term, but with a with a del square phi instead of just phi, right?
I see. I mean, I don't know, but maybe. I mean, I'm not done yet. But
yeah, the main point is that in scattering amplitude, while you are computing scattering amplitude, you impose equations of motion, and when you are imposing equations of motion in the terms of official Lagrangian, a field redefinition relates. All the field redefinitions are taken care of by just going to on shell, basically.
I see. Okay.
Yeah.
I see. So imposing on shell will, I mean, sort of ensure that, I mean, while writing this partition function, you will impose on shell condition, and therefore whatever n of m that you get your
equations of motion. I will impose equations of motion.
Okay.
Yeah. So first let's apply these things in steps, and first so gauge invariance is more or less, I think, clear that we want a color singlet as well as a Lorentz singlet in terms of photons, say, and then what is left is S4 permutations. So what is this S4 permutation? The total S matrix must be S4 invariant, right? And what we want, what we do is that we notice that S4 has a normal subgroup, which is the simultaneous exchange of two particles. These are generated by these generators, P12, P34, P13, P24, and so on. And they leave the Mandelstam invariance unchanged. Right? So it's better that we label our S matrices by their S3 properties than just, fully symmetrized S matrix, S4 invariant S matrix. And sometimes these are also called quasi-invariant S matrices, where you just have imposed the Z2 times Z2 invariant. All right. And since this S4 is a semi-direct product of S3 times Z2 times Z2, there is a non-trivial action of S3 on Z2 times Z2. That is just technically just some technicalities. What I mean to say is that we have some photon. We want to classify some photon and scalar S matrix. They can be decomposed into two distinct categories: Z2 times Z2 invariant and Z2 times Z2 non-invariant polynomials. And you can finally construct your Gluon S matrices by this in this manner. This M invariant is the usual tensor product of your photon S matrix and scalar S matrix, and this non-invariant is this weird Z2 times Z2 non-invariant thing that you have. All right, and you must also take care of the remaining S3, right? And what we will see is that this partition function that I told you about, they nicely break up into representations of S3, basically partition functions of S3. So from there, you can immediately read out what is the transformation property of your Lagrangian or your S matrices that you are supposed to get. So that coupled with the explicit expression is enough to tell you what sort of tensor structures that you can write down. Is that clear? Any questions?
Sorry, all your S4s and S3s are exchanging external particles, right?
Yeah.
Okay. And Z2 is like you take pairwise and you.
Yeah.
But which
Two
Z2 to
Z2s like
two
this.
Z2? So you
These are the generators.
Okay, fine. So the Z2s you fix initially, like how do you want to pair them, and then classify.
Right.
Yeah. Okay. Thanks.
Right.
Yeah.
Right. So, like, I mean, this slide is just for some terminology. Like, I mean, it's just that, like, I mean, I can skip this if it's already too late, I think. Like, so how much time do I have? Another half an hour?
I think about half an hour
Yeah.
typically. So
Yeah.
I'll leave it up to you.
Yeah. So let me just tell you that, like, there is some interesting maths structure, mathematical structure in this thing, this quasi-invariant S matrices. So these quasi-invariant S matrices, they don't, they form a module over the ring of polynomials of Mandelstam invariants, which means that you can multiply them by polynomials of ST and U, but you can't divide them by polynomials of STU. There is a hierarchical structure between this. All right. Basically, in terms of Lagrangians, you can think of this as like you can put contracted derivatives on your local Lagrangians, but you can't divide them by a 1 by box. That is something which is not allowed. All right. So there are many questions in the chats. I have not kept track of the chat. So please, like, if there are any questions.
The chat is me just talking rubbish, so you can.
Oh, I see. Madhu, you're not listening to my talk. I'll remember this.
I've been listening the whole time, but yeah, okay.
So basically, like, so there is a one-to-one relation between the S matrix and the local Lagrangians. This is referring to Anish's question, that we see that two Lagrangian, which they generate the same S matrix if they differ by total derivative, and they can be related to each other by field redefinitions and equations of motion. So there is a one-to-one map between equivalence classes of local Lagrangian and S matrices. Anish, is that like, does that answer your question? Like,
yes.
Yeah. So this is how we do this. Well, like, for gravitons and for gluons, there is this additional complication, because you see these are nonlinear in gauge fields or graviton, like gravitational perturbations, right? But even then, you can associate a equivalence class of four gluon or 4 graviton Lagrangians in this manner. Right? And that takes care of possible 4-point functions that you can get from, say, Yang-Mills as well as the F-cube term. Right? I will I'll show that. Like, so a part of this program has already been done. Classification of the photon modules has already been done by us in some previous paper. And what we do is, like, completely list all the possible gauge invariant local Lagrangians that can give rise to these S matrices, and like, including terms in lower dimensions, which include parity odd structures, explicitly, very explicitly. And, like, and we also list their S3 transformation properties. I'll show some examples in the next slide itself. And so, just to give you a flavor, for parity even and large D, we find that there are 2 4-derivative generators in transforming in what we call 3 of S3 representation, and 1 6-derivative which transform in a symmetry of the S3 representation. Right. So forget all this if this is too hard. Just look at equation 12. So these are the set of generators. These are the set of local Lagrangians that gives rise to your 4 photon S matrices. All right. And all other S matrices that you can write down will be a linear combination of some Mandelstam invariant, polynomial of Mandelstam invariant times this, times some other polynomial times this, times something like this. This is exhaustive. Like, there are no other generating structures for 4-point scattering amplitudes. And what do I mean by something which transforms in a 3? So let's try to label this trace F square in terms of particle levels. So you have this F1, F2, F3, F4, and this thing. S4 means that you have 24 such structures, but you will see that they just reduce to these 3 structures of this thing. All of them are equal to this, right? All the 21 other structures. So this is what I meant by something which transforms in a 3 of this thing. When you put on particle levels, there are 3 distinct structures which you can write from a particular Lagrangian. And what I mean by 1s is that you take this is fully symmetric Lagrangian. You can put in particle labels anywhere you like, and you will get the same result. All right. And finally, like from this this equation 13, what you do is that you to get the full S matrix, you just project onto S3 singlets, which is basically taking the sum of all 3. Right. So this is the crash course on how to go from how we construct modules to explicit S matrices, module counting to explicit S matrices. Is there a question? Any question?
Yeah, so I didn't quite understand the module structure, sir. So yeah. Is it like by applying the generators that you showed, like I, P1, 2, P3, 4, you can go from one module to the other?
No, sorry. What I meant was that in the module, the module was a ring over polynomials of S, T, and U. So you construct descendants in the module. Think of it as the Virasoro module.
Okay.
You construct the equivalent of Virasoro generators, the L zeros, L minus 1, L0 is this polynomials of S, T, and U. So given the Lagrangian structure, say trace F square, you multiply it by some polynomial in S, T, and U, all right, which means you put some contracted derivatives on trace F square and trace F square, right? And that is your descendant in your descendant of your module. Is that clear?
Okay. And so the 3 terms that you have written down in equation 12.
Yeah.
So I mean, in a simpler language, can I say that these 3 terms they are independent of each other?
Yes. They are completely linearly independent of each other. These are 3 independent generators of your photon module.
Okay.
And you can construct your module descendants by acting on these Lagrangians by contracted derivatives. So you can just do it.
Wherein the argument was the fact that D should be greater than equal to 5 necessary until now?
Oh yeah, because the point is that in no. What I'm saying is that like if you take D less than 5, there are many other modules which come because they are specific to dimension. What I'm saying is that for large enough dimensions, the results stabilize. There are no, it does not grow with this thing. So essentially, like a seemingly infinite problem has been truncated to just classification, like classification 3 terms in 12.
I see. But if you're saying that for let's say D equal to 5 and above, there are only 3 terms, but suddenly for D equal to 4, I mean, there's like a significantly higher number.
No. Just one. I think there are some parity odd terms which appear, like with epsilon tensors, very specific to those dimensions.
Okay.
Not a significant large number. The generators change by 1 or 2. I think like that's it.
Okay. I think you can have this FF tilde in 4D. Like you mean something like that, like square of that thing.
Correct. F wedge F type.
F wedge F. Okay.
Right.
Trace F wedge F, trace F square sort of term.
Okay.
And so now, like, so one part of our classification is already done. Like the photons, we know how to classify. Now we have to take care of the color structure. So how do we do that? This structure is way simpler than classifying the photon module actually, because there are no derivatives acting on the color structure. Like it's just some group theory singlet that we have to do. So if like, for example, like if we denote the color representation of the gauge group G given by rho, I mean the Z2 Z times Z2 invariant singlet in the tensor product of 4 representations rho of the gauge group G is given by this character form, but this formula, group theory formula, given in 14. Sorry. given in 14. All right. I'm not explaining how I'm getting this formula, but like, I mean, okay, let's see after the talk if I have time, I can tell you roughly what how to get this color, this formula. But essentially, like, if you evaluate number of singlets in the tensor product of 4 group theoretic representations row, you are done basically. And we have been able to do it using some online LEAR program. All right. So let me just do this, and like these are the results, right? So counting of S3 representations tell you that if your gauge group is SON, your fields are charged under adjoint of SON, and for n greater than 9, there are 2 generators which transform in the symmetric representation of S3, and 2 generators which transforms in the representation of S3. And similarly for lower dimensions. All right. So this is the group theory argument that that we are doing. And similarly, the Z2 times Z2 non-invariant singlet you can build out of such a character formula also. And this is the result. So for SON, for very large n, there are no such structures. For n equals 6 and n equals 4, there are some structures. And for SUN, only for n greater than 3, you have such a structure. There's nothing for n less than 3. So that's a counting problem. How do you explicitly construct your scalar S-matrices? So if you take phi's to be your this gauge group generator, the Lagrangians which generate these are given by this trace phi phi, trace phi phi. All right, and then for SON, the second one is also given by this. Similarly, for SUN, it's also same, but unlike SON, where this single chain of trace is automatically Z2 times Z2 symmetric, this is not so here, right? And we have a systematic classification for lower n. Similarly, one can also construct the non-invariant modules, and for example, in SO6, because of the existence of this special epsilon tensor, you can construct these Z2 times Z2 antisymmetric modules. What do I mean by that? It means that if you apply Z2 times Z2 transformations on this, it will vanish. So this needs to multiply with something which is also another Z2 times Z2 invariant to make sense, basically. And for SUN also, you can construct these modules. And so basically, like, so you also need to construct the photon non-invariant modules, and this is difficult, and like, I mean, but we have been able to do it through mostly trial and error, but we have a check against it, which I will come to. That is the final check of all our Lagrangian structures. It's a symmetric, similarly for photon modules, for large D, there is a non-invariant structure, and many such non-invariant modules exist for lower dimensions. I'm not listing them, but they're there. And finally, we are in a position to tensor all of them together. All right. So, for example, like the M invariant would be a tensor product of this scalar module times the photon module. You see how I'm tensoring this? Like, I'm taking I hope this tensor product is clear. Like, is this clear, or are there any questions? I'm assuming there are no questions. So M non-invariant also, you can do such a tensor product. It's not very intuitive, but you can convince yourself that this is the Lagrangian which corresponds to that module. And we have a complete listing done for all n and for d greater than equals to 8, right? So how do I know all this is correct? I mean, I'm doing some counting, I have motivated some group theory principles. How do I know this? So one thing is that, like, we note that the local Lagrangian, they are characterized by their momentum dimension, that is the number of momenta we have, and their S3 transformation properties. So basically I can write down, as I was saying, a partition function encoding all this, right? So for example, for trace f square, I can write down a Z S matrix, which is like this. So you can put in many derivatives on trace f square, and suppose your total derivative number of your tensor structure is say m. You want to know how many independent, linearly independent S matrices are there, all right, at this level. I can expand this thing and look at the coefficient of x to the power m and tell you, oh, you can sprinkle derivatives on trace f square at this derivative order in this many ways. All right. So this is purely from the module counting. Like I have constructed the module, I have noted down their S2 properties. I am proposing this ZS matrix. Now I will come to the checking part. How do I do this? Well, one can do this, but by something called evaluating a like a SOD matrix integral. So you can think of constructing gauge invariant, Lorentz invariant, uh, local Lagrangian built out of 4 gluon field strength tensors, right? And this is well known, this is well studied. Basically something which is called a letter partition function. You consider a multi-particle letter partition function of gluons and then perform a SOD integral, taking into care the singlet condition for G, equations of motion, Bianchi identities, as well as total derivatives. This all can be done in a linearized fashion. And you get a different way of constructing the same ZS matrix. But now you know what your local Lagrangians that they correspond to. And we obtain a perfect match between M invariant and with M invariant and M non-invariant in this group theoretic manner. Is the checking clear? Like, or is it?
Yeah.
So this is I'm just showing you some result like that. You can have a nice table of partition functions that tell you how many, the degrees of freedom in your S matrices. And while these were local S matrices, and our conjecture, well, not conjecture, it's almost implied that you just multiply these modules or S matrices by non-analytic functions of ST and U, and you will be able to generate pole pieces, or even, for example, I think I'm not sure, but I think you will be also able to generate the other non-analytic structures also, like log S or something. You just multiply it by log S and this thing. And we have been able to express the Young-Mills amplitude or gluon amplitude with gluon exchange in terms of our basic structures. It's a bit complicated, so I have not shown it, but yeah, it can be done. So that completes my classification of this thing. And what I have done is that we have first proposed that the gluon S matrix must be something like scalar times photon. And then we have systematically, since the photon was already done, part of the photon was already done, we did the calculation for M scalar and also M photon in terms of the Z2 times Z2 non-invariant module. And we verified our calculations through a explicit letter partition function, which tells you the local Lagrangians which gives rise to these S matrices. So there is a nice check of our conjecture. So what are the future directions? So now in HPBS, the local scalar S matrices, just like I did for photons, the gluons, you can do the same for scalar S matrices. They give rise to truncated solutions, that is solutions having support over finitely many spins of conformal crossing equation. And so one can expect the gluon S matrices also to give rise to truncated solution for non-abelian currents. Right? As a zeroth order problem, what we are trying to do with what I'm trying to do with Kaushik is now whether I can extend the scalar case to colored scalar equation, because that's much easier than gluons. And and also maybe to fermions to check this local duality, local bulk locality business. And in our classification, this factorized structure plays an important role. So it's tempting, although I'm not sure, that it might lead to some generalization of the BCG relation between gauge theories which are different from Yang-Mills and gravitational theory which are different from Einstein gravity. We don't know how to approach this problem, but I would love to hear suggestions since many of you have worked on these things. But yeah, essentially we have classified you give me any photon gluon S-matrix, I'll be able to write it down in terms of my basis structure. That is my claim here. So like I'm essentially done. Like if I can take questions. If
okay, let's thank Shubham for that talk. Okay, questions?
Can I ask a question?
Yeah.
So I mean, maybe I missed this, but I thought the conjecture was for gravitational particles. But
yeah, I'm not saying anything for I'm just doing the classification part. So that's an interesting question, because so far what we have. So for example, like it's tempting to guess that Yang-Mills is the only allowed gluon Lagrangian from some physical principle. But this Rege growth conjecture, that is not sufficient to rule other, say, trace F cube term out. All right, you need something more deeper conjecture. People have not done it. Like, I mean, I don't know of any such conjectures. Like, I mean, in principle, like there is a zeroth order question to be considered. Like, can one say anything about 3-point couplings at this level? All right. So, for example, like what I'm trying to say is the following: that we know this average null energy condition, right? That expectation value of the stress tensor integrated over null infinity in between CFT states must be positive. That leads to a constraint on correlators of the form JJT or TTT or higher spin stress tensor. All right. One would first like to have a similar conjecture for gluon, like expectation value of say J or something like that. I don't know what that.
I see.
Right. That is not there. Forget about 4-point functions. Even at the 3-point functions, there is a question. Like, can there be some ANEC type arguments or constraints on 3-point functions of gluons? As far as I know, there is none. So
I see.
Yeah. But yeah, I don't know how to this thing, but like as far as I know, like Maldacena had one paper where he tried to do it via some conservation of charge at null infinity or something like that, but it didn't give some like very strong constraints as far as I am aware. I have to see, but yeah, maybe some modification of that can work. I don't know. Yeah.
I see. But because from the, I mean, again, this is another thing that I don't know much. I'm just like speculating and stuff. But from this whole KLT or double copy kind of things, I mean, if you say that Einstein gravity is sort of the unique S-matrix, I mean, there should be something similar for Yang-Mills.
Sorry, I missed the question. Sorry.
I'm saying that if you can make a statement that Einstein gravity is the unique S-matrix.
Yes.
Then I mean, and because this is only 3 level, wouldn't you be able to make something about Yang-Mills using some double copy or this KLT kind of things?
Well, like, see, double copy is not a constraining, like.
No, I'm not saying using that. I'm saying as a intuition, in the sense that there might be something that would.
Right. There should be, but I'm not sure what exactly it is. Like, for sure, like the conjecture that we are putting forward now, that scattering amplitude of any spin must grow slower than a square. That is certainly not enough to constrain Yang-Mills. Like, You can have trace f cube term as well as some trace f to the power 4 terms allowed by that conjecture. All right. What you probably want is something more not of in that direction, because this growth conjecture, like roughly speaking, depends on the derivatives in your S matrix. So you see, like up till fourth derivative order, any S matrix roughly is allowed, right? Whereas from Yang-Mills, you see, like you have the Yang-Mills amplitude is roughly what I mean, zeroth order in derivatives, right? Because you have two derivatives and then by 4. So in that sense, like there is a wide gap between what the bound is setting and what you have in between, what you actually want. So that line of argument might not be possible, but some other kind of, maybe some charge conservation or something like that, some other kind of thing must be there. I'm not sure what. But as a zeroth order thing, maybe one can try to do some thing related to 3-point function, because that's how the gravity thing also worked out. Like CMZ imposed some condition on the 3-point functions. Then came the chaos bound, which is the 4-point function. That's some sort of idea that I'm getting at. Okay. Yeah. But certainly there might be, this double copy certainly suggests that it has to be perhaps unique. But yeah, I don't know a priori how to quantify into something calculable or something.
Okay. I see.
Shubham, I have a question.
Yeah.
So, is there something that can be said about the color kinematics duality? Not the double copy per se, just like if these numerators, so you have all these ST and U channels, so the numerators corresponding to them, do they satisfy the same Jacobi entity as the color structure?
Yeah, well, one has to see. I have not thought about this actually, like, because I don't know maybe it would be good to talk to you actually, like, because I personally don't know the BCJ relations that well. I just started reading recently, and with my limited knowledge, I don't see how that might happen. Maybe if we can talk sometime.
Yeah, that would be good.
And I can tell you about the structure that I am getting. Maybe you can just say whether it's following something.
Definitely, yeah.
Shubham?
Yeah.
So I just have this. It's related to that thing that Anish was asking. So in the CEMZ paper, the argument was based on this time advance Shapiro delay, right, or advance, depending on. Like these shockwave solutions, they have like so they're classical solutions in gravity.
Yes.
And they do single copy to solutions in Yang-Mills theory. But I'm just wondering how. I mean, you can't have a time advance, time delay argument there.
What is the physics that is happening?
Yeah. So that.
My impression is that it must be some kind of charge conservation. Maybe some kind of,
Why are you saying charge? I don't understand this at all.
Because what I mean with color charge conservation or something like that. Because that's the only thing that is there, right? I mean,
right.
Like some, like after going across the shock wave, do you see any funny stuff happening in the 3-point vortices or something like that?
I see.
I don't know what I'm talking about. Sorry, I should not. But like I mean, certainly it's worthwhile thinking about what the 3-point function might be, and like I think like before going to for gravity, I can tell you of the linear sequence of progression in this condition. So first came Maldacena and Hoffman collider bounds, which is a generalization of Anek. Right? Anek tells you that, all right, you can have R square and R cube terms in your bulk theory, and this will still be a unitary theory. Okay? Unitary theory. Then comes CMC, right? Which tells you that, okay, if you have R square and R cube, I don't care about unitarity, this won't be causal because you are violating some physics scattering amplitude, some scattering. It's giving you some nonsense in some Gedanken experiment, right? Then comes the chaos form, which is like extending it to 4-point function, right? Now, for gluons, even this equivalence of the equivalent thing for NA is not known.
Right.
After that, CMZ might be there, equivalent of CMZ. You see, like there might be a hierarchy of things that one has to consider. Like first, you even like not saying that okay, Yang-Mills is the only general thing. How can it be possible that you can have arbitrary number of 3-point couplings in the bulk? What is the way to rule them out, or this thing? Something like that,
Right. I mean, so along those lines, since the ANEC concerns itself with the sort of integrated stress tensor, would it be something like in the gauge theory? Would it be like an integrated current?
Yeah. I think so. I think there are some proposals regarding that. Maldasena's paper, the initial paper on ANEC, but they did not make it concrete. Like in the sense that I think they didn't get some very qualitative bounds, or the physics was not working. Yeah, I mean that thing is still open actually. Like
I see.
Yeah.
Okay. Thanks. Any other questions?
Shubham?
Yeah.
So will you speak about, or did you speak about supersymmetry? Like for 2 minutes, I was not there. Like, will that restrict if we demand like some amount of SUSI to be there?
I would expect so. Yeah. Usually, at least for ANEC, I know that supersymmetry like hugely cuts down the allowed regions of this thing. But yeah.
Right. But like to begin studying that, do you think like there is some obstruction, or like is it just a matter of doing it?
So depends on what are you exactly, how are you framing the problem? Like what do you mean by including supersymmetry? Like
okay. What I mean is you have this classification of like various terms that can appear in the Lagrangian, right?
Yes.
But in a supersymmetric theory, like you will have different terms only in some combinations, like not all of them.
Correct.
Be allowed.
Yeah.
So if
I think like that sort of classification can also be done. Yeah. Right.
Okay.
Yeah.
Any other questions?
Yeah, one small question.
Sure.
So, I don't know if this is probably a stupid question, but how does the chaos bond, which is related to out of time ordered correlators, lead to a bound on like scattering amplitudes, which is like time ordered?
Yeah. So like this is a very convoluted argument. Nevertheless, I'll try to say as clearly as I can. So out of time ordered correlators in thermal CFT can be related to say to certain kinematic configurations of 4-point correlators of a zero temperature CFT. This is the first step. All right.
Okay.
If you put a zero temperature CFT on a, you will get I mean, it's the same thing basically. It's just a change of coordinates basically. Okay.
Okay.
Thermal CFTs are equivalent to zero temperature CFTs on Riedler wedge with a particular temperature. Right?
Okay.
Beta is equal to 2 pi.
I see. Okay.
Yeah. Now the CFT is, if it's a Lagrangian CFT, it's dual to some bulk scattering process, right?
Right. Yeah.
Now that, and we are just looking at the kinematic configuration of the bulk scattering process also in the flat space.
Oh, okay.
So it's a very convoluted argument.
Yes.
But like we want a more straightforward, but usually like trying to put constraints on flat space scattering amplitudes is very difficult. Like lots of people have tried, and like as far as I know, like at least nothing has been no significant progress has been achieved except the fact that it must be growing polynomial like in S. That is this Gribov bound, like the dispersion relations, like in order to have dispersion relations in your scattering amplitudes, you need the amplitude to follow at least polynomial, but nothing of the polynomial bound which is allowed. Like as long as it's polynomial, even if it's s to the power 100, it's fine.
Okay, there's no higher bound.
No. It's not higher bound. There is no higher bound. From at least this S-matrix bootstrap or S-matrix theory of the 60s, there has not been any bounds like that. So this must be very hard. Like I mean, since you're working on this Cry plus and like that.
Okay.
Yeah, but that is the ultimate aim, like to get this bound from that sort of an analysis where you are just looking at flat space without referring to any CFT or bulk or anything.
Right. Yeah.
Okay, are there any other questions? Okay, if not, then let's all unmute ourselves and thank Shubham again.